All right, I assume everything is set up. I hope everybody can hear me in the room and online. So, good morning, everyone. I'm Fabian. I'm a PhD student about to wrap up my thesis very soon from UPC in Barcelona. And I'm going to present to you today our package that we developed on lifecycle optimization called PULPO. This was developed in collaboration with people from Zurich, Professor Gonzalo Guillen-Gonzalez, and Robert Istrate, who is now working in CML in Leiden. And yeah, let's start off by talking about what is lifecycle optimization. I don't think I have to explain to anybody the phases of lifecycle assessment. And there's, when you look into the literature, there's like two sort of paradigms when it comes to lifecycle optimization. One is what I like to think about as lifecycle assessment-based optimization. This is typically performed in engineering tasks, where we have our rather complex, more or less granular system models. Here I'm putting an example of a reaction and separation system from chemical engineering. And then we're taking as inputs the aggregated indicators that come from lifecycle assessment. We plug them into our complex optimization problems as auxiliary equations and parameters. And then we're able to design our systems not only from economic, safety, or resilience point of view, but also from environmental point of view, which is great. And I don't have anything against that. We should do that. But there's another paradigm, if you look into the literature, that is more LCA-centric, that doesn't export the data that we're handling in the LCA sphere and use it in other models, but rather directly optimize on top of the lifecycle inventories. There's many ways you can imagine this, but I like to think of this as a repeated inventory analysis impact assessment step. So what we typically do, or what LCA practitioners typically do, right, is creating their inventories, assessing the impact, interpreting them, and eventually iterating through these phases to get results and interpret them from the LCA. Now, in LCA, there's several approaches to go beyond that. We have sensitivity analysis, we have scenario analysis, right, to look in different configurations of our lifecycle inventories. Now, what you can do with optimization is specify an objective, an impact category that you want to minimize, and directly find those inventories that would minimize this impact category. And you can do this in the foreground or in the background, but we'll talk about that a little bit later. Now, what can be done with PULPO? This is just an example that I would like to bring up. So if you would like to know the impact of methanol, you have many, many ways of producing methanol, right? You could do this with by converting CO2 with hydrogen to methanol. You could do steam methane reforming using fossil raw materials, or using biomass as a raw material, right? And there are several choices that you can do along this supply chain. If you do CO2 plus hydrogen, where does the CO2 come from? Where does the hydrogen come from? Which electrolysis do you use? Which source of energy do you use to run your electrolysis? So obviously, you can do a life cycle assessment of a single configuration of that. You get the impacts, and that's it. But you could also try to ask the reverse question, which is, which would be the necessary structure to minimize my impact category, while at the same time fulfilling my final demand of methanol. Okay, so there's many choices, and there in real life there can also be constraints, right? If we go, for example, through this biomass pathway that uses woody residues from Germany as an input, you may have availability constraints on that. There is not enough available biomass residues to fulfill your complete final demand for methanol. And these are things that are very natural to introduce once you think about optimization rather than assessment. Okay, getting to PULPO. PULPO is an acronym, was proposed by my colleague Victor. It stands for Python-based user-defined lifecycle product optimization. So it has the key concepts of lifecycle and optimization integrated in there. And for the non-Spanish speakers, this means octopus, as you might guess from this little logo here. And I would like to show you how the information flows in Pulpo and how do you actually set up a problem with it. Most importantly, you start off with a goal and scope, as in any regular lifecycle assessment. You also specify there the functional unit. You have to specify an objective function that can be any impact category, as we will talk about later. Then you have to specify the choices that are the degrees of freedom in your inventory. And finally, you have to specify constraints if there are constraints. Okay, what Pulpo then does is with these specifications, it uses Brightway functions to retrieve the necessary data from the databases that you are managing with Brightway, right? This can be any database from any project that you might have stored on your computer. It can be user inventories. Whatever you have stored in Brightway, you can retrieve and use as a backbone for optimization. And this includes also the characterization factors that you might have stored in your projects. Having all of this data, Pulpo then creates the optimization problem using another open source Python package that is called Pyomo. Might be familiar to some of you. It's a very powerful package that is often used in engineering disciplines as an alternative to commercial software like GAMS. And in Pyomo, we're constructing and solving the optimization problem. Currently, you have the option to choose between two different free open source solvers to solve the problem, Higgs and IPOpt. But we also have an interface to GAMS. So if you happen to have a license for GAMS and are subscribed to some solvers, you may also use them. Like usually Cplex works very well for these linear problems that result from Pulpo. Okay, having resolved the optimization problem, the results can be saved in a spreadsheet or summarized in the console or in the Jupyter notebook. Great. Let's talk a bit more about these 4 things that are key that have to be specified by the user of the tool. Now, the functional unit can be anything, like in any LCA, can be electricity, cheese, shoes, whatever, right? The objective function can be any impact category, as I mentioned before. As long as you have it in your Brightway project, you can use it as objective to minimize. Then you have the choices that are key to the concept of optimization. These can be are typically product equivalent processes. So processes that produce a product that can be that cannot be distinguished by the way it has been produced. I think we had the example the other day about electricity. You plug your phone to the socket, and you do not know where does the electricity come from, right? And it is not your choice. For you, this would be like a background process, right? You don't really have the choice to say, I want the electricity from the wind plant or from the coal plant, right? But for other people, this might actually be a foreground choice. The people who are taking the decisions about which technology to invest into and which to construct. Okay, and aside from the choices, you have to introduce constraints that can be any sort of limitations. It could be availability of resources, capacity constraints on production processes, environmental regulations, you name it. Okay, I'm going a little bit deeper on 3 of these concepts before we actually go to execute some code. So I'm sure that most of you had at some point have to find minima or maxima to some function in high school or in college. And Pulpo is doing exactly that with the objective function. The objective function is, though, a little bit longer term than what you might be used to, but hey, it's linear at least. So what you have in there is a summation of the characterization factors multiplied with the scaling vector, and eventually we have the option in Pulpo to allow a weighted sum of the objectives. So you can not only minimize for one category, but you could find a balanced trade-off solution that balances, for example, climate change category with a human health category, let's say. Okay, let's move to the choices. I would like to briefly mention how this is realized mathematically in the background, under the hood. So what we typically have in LCA is this square technosphere matrix, right? This is just a very simple example here. And what we're solving in the first step is the A times S equals F equation, right? And due to the structure of the A matrix, which is a square and non-singular, there's always a unique solution to that problem. Now, the way that we introduce choices now mathematically is by summing up the rows of the product equivalent processes. By doing so, we cannot distinguish anymore, or we do not presuppose which process is going to be used for providing that product, but we let the solver take that decision. And what we end up with then is a rectangular matrix, as you can see here. And this system has, in principle, infinitely many solutions, which is why we need an objective function to drive our system to the desired solution, which minimizes our impact. Okay, finally, about the constraints. Currently, we have the option to put upper limits on the scaling vector, on the impact vector, and on the environmental flow vector. Depending on the type of process that you're constraining, you could interpret this in different ways. So if you put, for example, an upper limitation on a market, this could mean that your availability of this product is constrained. If you put an upper bound on a wind farm, let's say, you could interpret this as a capacity constraint of this particular unit, right? So we give the user a lot of flexibility in the way that they can express real physical and regulatory constraints that might be in their system. You also have the possibility to put lower limits, but I'm not gonna talk about that now. Okay, so to wrap it up, we have this optimization problem formulation. It is parameterized by the data from Brightway, by the data that is supplied by the user. You throw PULPO at it, you let it do its magic with Brightway and PyOmo, and you end up with an optimized system. Now, let's move to the notebook. And I'm sorry for using so many slides. This is my first Brightcon, and I learned the better now. So if I come back, it will be less. Okay, so to get to the notebook, I think we have to, you have to go to hub.brightway.dev. You update, well, if you have already updated the one from Chris before, it will already be in the newest version, because we updated it this morning. Then you go to talks, to Friday, PULPO, and you see there's a lot of material. So this is basically prepared for a one-day, I would say, class, but I had to limit myself. So let's look at notebook number 2, which is a tangible example that we just walked through together now. So in this example, we have a production system for rice. This example comes from a paper that I would call the parent of PULPO. Is the technology choice model that was developed by people in Aachen. And I learned on Wednesday from Timo that they actually have a course on LCA, and they teach a little bit of optimization in there. So I would be happy to learn if other universities are also having optimization actually integrated in their LCA courses. Anyway, so this is the production system that we're looking at. Our functional unit is going to be processed rice, which comes from the rice factory. The rice factory has several inputs. On one hand, it has unprocessed rice, which comes from the rice farm. We need process heat, which can come from 3 different types of boilers. So this is one kind of choice that we have in our system, where to source our heat from. Then we have some electricity and transportation inputs also. Okay, and as I mentioned, we have the 3 different types of boilers. And one of them is a rice husk boiler, which has as a raw material rice husk, which can be sourced from various zones that are in different distance to our rice factory. So the rice husk from zone 5 is the furthest away, and rice husk from zone number 1 is the closest. And there we have a sort of regional choice. Which region should we source our rice husk from? Okay, and then there's a curiosity here, which is actually not only a curiosity, because it's a very powerful feature of optimization. That is, rice farming is a multifunctional unit. So it produces both processed rice and rice husk as a byproduct. And optimization can handle this multifunctionality without the need to perform allocation. The way that I currently implemented this is a bit hackish. So I hope that I can in the future use the multifunctionality tool to do that. But you will see how this is implemented right now. So let's then proceed to do the goal and scope definition. First, the functional unit is 1 megaton of processed rice. The objective function for now is minimizing the global warming potential. The possible choices are the ones that I mentioned before. We have a regional choice and a technology choice. Then we have, and for now, we don't look at additional constraints. Along the notebook, we will add progressively more constraints to the problem. Here you can see the already rectangularized technosphere matrix. You will notice that there are rows where you have more than one positive entry. That is the row that corresponds, for instance, to thermal energy that comes from the natural gas boiler, the rice husk boiler, and the wood pellet boiler. And the same applies for the rice husk at factory, which can come from the 5 different processes that provide the rice husk that comes from the farms. And here you also see that the rice farming column, the process rice farming, is multifunctional, as it has both a unprocessed rice as an output, and also rice husk at farm as byproduct. Okay, and this is something, the biosphere is something that will also be fixed in the future, because the way that we have here CO2 and CH4 as environmental flows. So far, so good. And then I have another row, which is economic flows. So maybe this is a sin, but this was the hackish way for me to introduce another indicator that is not environmental into our optimization problem. The way you would typically go about this, I guess, is through some price vector. But for now, this is the way that I introduced economic information into the problem by having it in the biosphere. And then we have the characterization factor matrix. Great. So this is implemented in Brightway. There's a function to set up the database. You can actually explore it in Activity Browser, because the database is created in Brightway 2. So you can actually look at it, but I'm planning to update this to include Brightway 2.5 functions, databases created in Brightway 2.5. And now let's move to actually execute some code, right? We have the problem defined now. First thing is importing PULPO. I guess I should maybe restart the kernel. Okay, we import PULPO, then we import some other packages that we will need later. And then the first thing is to specify where is our data located, right? In this case, I think there's something missing here. No, sorry, I think this is not correct. So if it doesn't work for you, it's please let me know, but here it works. So you have to specify the location where the data is located. In this case, it's a project called Rice Husk Example, and the database is Rice Husk Example DB. You have to also share the name of the method, the impact category that you want to minimize. Then you also have to specify a path where you want to store your results, if you want to store them as an Excel file. And then we are finally at the point where we can create a PULPO worker. Well, I call it a PULPO worker usually. That is an object of the PULPO optimizer class, which handles all the interaction with PULPO. Right, you have to give it, you have to specify where's the project, the database, etc. And then you retrieve the data by calling get LCI data. Okay. That loads basically the A, B, and C matrices from Brightway into memory. And then next step is to define the demand. You have to specify somehow the demand, and the way that we're doing that in PULPO right now is via a dictionary. First, you have to retrieve the processes that correspond to your final demand. In this case, it's the process that has as a reference product processed rice. There's a function in PULPO which is called retrieved processes. It finds this process, and then you specify it in the dictionary here. Here we specify that we want 1 megaton. Everything in the inventory is scaled to megatons, so I just put a 1 here. So we have our demand specified. Then we have to specify the choices. And we go about this in the same way that we do it for the demand. First, we have to find them. In this case, it's the rice husk collection 1 to 5 and the 3 boilers. Please ignore this for now. This is the way that I'm currently handling multifunctionality, and I don't want to dive into that too much. But yeah, then we put all of this together in a dictionary. You have to give a label to the product equivalent processes, in this case, rice husk and thermal energy. And yes, it's a nested dictionary. You specify the choices. And then we can finally instantiate the optimization problem. We do this with the PULPO worker instantiate call. We have to give it the choices and the demand, and then we can solve it. So this is super fast. This is a very small, super small problem, so it's almost instantaneous. And we're using Higgs solver right now, the open source one. And then we can save and summarize the results. So now we created an Excel sheet, rice example unconstrained, which will be saved in the directory that we have specified in the beginning. And we can summarize the results as you can see here. So what PULPO tells us now is that to produce 1 megaton of processed rice, the minimum impact will be 0.858 megaton of CO2 equivalent, and use exclusively rice husk from zone number 1 to provide the thermal heat in the rice husk boiler. Okay, so zone number 1 is the closest one, if you remember, so it makes sense. So we don't want to go very far to get our raw materials. This will minimize the impacts. And we are producing more rice husk than we actually need, so the rest of it will be burned. This is the way that the optimization now handles the multifunctionality. We're producing more than we actually need, so we somehow have to get rid of the byproduct. Great. Probably most of you are, or many of you are thinking right now, hey, I could have done this manually, right? And this is the beauty of an example case, right? It shows you how to do something in a low and low complexity scale, but then you can eventually apply this to much more complex cases. But I bet that the next thing wouldn't be so trivial for most. That is, what happens if we have actually constraints? Now, the first constraint that I want to look at is availability of rice husk in the different farms. Let's say in each of the farms, there's only a certain quantity that they are able to provide you with. What happens then? And now I'm putting an arbitrary value here of 0. It's half arbitrary because I wanted my results to look in a specific way. 0.03 megatons of rice husk available in each zone. We specify this within the choices dictionary. Before, we had here very high values after the processes. This was like, I think, 10 to the power of 10. This is my hackish way of saying this is unconstrained. Just put the constraint very high, so we will never activate it. So now we lower this value to 0.03. And we actually will see some constraints in the results. So we instantiate, we solve, blah, blah, blah. And then we find that now the minimum impact is a little bit higher. Before it was 0.8 something, now it's 0.916 megaton of CO2 equivalent. So constraining our system makes it less efficient. And then we also see that the rice husk is now sourced from 5 different sources. It uses rice husk from everywhere as much as it can. And on top of that, the remaining energy is going to be supplied by the wood pellet boiler. It's not enough with the 0.3 megatons of rice husk to run our process, to fulfill our final demand in the end. Now, I have added a couple of cases more with other constraints. This is putting an arbitrary constraint on transport. Like, why not? We can put constraints wherever we want in the system. So now I put a constraint on transport. And then in this case, we see that, oh, now rice husk is not sourced anymore from zones 4 and 5 because they're too far away. In order to comply with our limitation on transport, we can only go to zone number 3, 1, 2, and 3, and supply the remaining heat through the wood pellet boiler, which has a lower need for transport. Okay, and the final constraint case that I want to consider is putting a constraint on the supply of wood pellets for the wood pellet boiler. Now, let's do that. Now I'm specifying here a 0.1 megaton of limit to the supply of wood pellets. For that, we first have to retrieve that process. Then we have to specify the upper limit in a dictionary. We pass it to the worker via the instantiate function. We solve it, again, very fast, and we summarize the results. Now, with all of these constraints that we have added to the system, now the optimum global warming potential indicator is 1.26 megaton of CO2 equivalent, which is quite much higher than what we had in the beginning in the unconstrained case. And we see that not only does it source the rice husk from all the sources, it also uses now natural gas boiler to supply part of the heat, because both the wood pellet boiler as well as the rice husk boiler are too constrained to deliver the final enough thermal energy to fulfill our final demand for rice. Great. Now this is a summary of all the cases that I just went through very quickly. We have here the unconstrained case where the whole thermal energy is supplied with rice husk from zone number 1. We have the first constraint case where we have availability constraint on each of the rice husk zones. Then we have had the third case, which was a limitation on the amount of transport that we can allow. And finally, the most constrained case where we also had availability constraint on wood pellets, where we see that all the technologies are actually employed to deliver our final demand at minimum impact. Okay, so now I would like to go one step further, because I believe that what I just showed to you is something that would be super cool in a graphical user interface, that you can just drag and drop the choices that you want to specify. I'm thinking about activity browser or something. Yeah, I don't know. A graphical user interface would be very cool to do this kind of simple optimization tasks. Now you can also go beyond that and do some for loops and to do a little bit more complex assessment, let's say. And here I want to just briefly demonstrate you what happens if you vary the final demand. Right? Before we had 1 megaton of processed rice. Now we're doing that in a loop from 0.05 megaton to 1 megaton and see what happens to the technologies that are chosen. I'm not going to go explain all the syntax here in this, but it's very straightforward. You create a list of demands. You have a for loop. You update the value of the demand in your dictionary every time you instantiate, you solve, and then you extract the values that you're interested in. And this is something that needs a little bit more work from my side to make it easier for the users to retrieve the internal variables of PULPO. But for now, this is the way it's handled. We're doing this, and it's also very fast. It has already optimized the 20 times for all the different values of demand that we specified. And then we can plot the results in a similar fashion than I did before. And here now we have on the x-axis the final demand of the amount of processed rice that we want. And we can see how, depending on the demand that you specify, you get a different technology mix that provides this final demand at minimum impact. Always respecting the constraints that you are able to specify. Okay, and the last example that I want to show you is a multi-objective assessment, right? You remember I inserted some economic information at the beginning in the biosphere, so we can also take that into account when doing our optimization. For doing that, we have to pass a dictionary of methods in the first place. So, and this dictionary specifies how much weight do you put on each of the objectives. Here we're putting now 0 weight on the climate change category and full weight on the economic category. Then we're creating a new PULPO worker. We call it PULPO worker multi. We retrieve the data, and then we can rerun the problem. We instantiate it. It's again using the constraints from before, since we put them here as upper limit, and we can look at the results. Now, I think many of you can guess what is the result in advance, but we see here that now that we're minimizing economics cost, basically the minimum cost is I think this is 0.56 kilogram per kilogram of rice. Or right now I'm a bit confused about the scale of this value, which is something that I should have put in the description of the characterization factor. However, this is minimizing the cost of the system, and we're also calculating the climate change impact alongside, right? So the system that minimizes cost now has an impact, a climate change impact of 1.6 kilogram megaton CO2 equivalent, right? If you remember, this is much higher than what we have seen before. Before we had 0.8. In the constraint case, we had 1.2. So when you minimize economics, you have higher impact, something that we often see. And actually, the choices that have been done by the optimizer are the natural gas boiler, right? The parameters are in such a way that the natural gas boiler supplies the thermal heat at lowest cost, but at highest impact. Okay. Right. This is just one point. This is just, well, for now we have assessed the extreme points, let's say. We have assessed the global warming potential minimum and the economic minimum. But what you can do in multi-objective optimization is also reveal the trade-off curve in between those two objectives. We're doing that also in a loop. And we can achieve plots like this. So here we can see the entire trade-off between those two objectives. We have the minimum cost solution, right? The one that has a 1.6. Now I scaled it to I normalized the functional unit, kilogram CO2 equivalent per kilogram of produced rice, but at lowest cost. And here we have the other anchor point that is the lowest global warming potential, but highest cost. And here we can find the trade-off curve in between. That must not necessarily be linear, as you can see. This is non-linear, and there might be some processes that actually are neither optimal in any of the categories, but strike a nice balance, right? And via optimization, you can identify these processes that give you a nice trade-off in the objectives. Okay, I think I'm at the end of my, no, let me bring up a couple of last slide. So during the conference, I got many ideas, and I learned a lot about coding practices, how to manage repositories. So there's a lot of work to be done, and I'm looking forward to doing that once I start my new position after defending my thesis. Yeah, good documentation, repository management, some web app, and how to consider uncertainties and time-resolved inventories. This is something that is theoretically already understood how to do it, but we would need to implement it in the package and make it available to the community, right? And that's it from my side. Thank you so much for your attention. I'm happy to take questions, comments. Do I have to press here? Should be able to Yeah. Because he doesn't hear you. Sorry. Yeah, just whoever has a question online, just unmute yourself and ask.
Hi, Fabian. Very nice presentation. Thanks. I have a question and a comment. Like when you go from the square to the rectangular matrix, is it like if you were kind of erasing the information in the markets because you are kind of calculating the market as an optimum market, or because when you said that you were summing the I was wondering if there's no loss of information when you sum the squares.
Right. You're not losing any information on the processes themselves, right? We're looking at product equivalent processes, like wind farm or solar panels, but you're not losing any information on the individual process. What you're losing is the previous way that these technologies were implemented in the technosphere matrix. So before, these processes were used in certain markets in a certain share, right? But by summing up the rows, you're losing these shares and you're optimizing them. This is what you're interested in when doing optimization.
Yeah, what that was okay. I think I got it. Yeah, and the other thing is about the cost. I think you could use simply like the value added, which are already is in the biosphere, or it was there. And if you sum all the value added, like any other with an impact assessment method that adds the same weight to any kind of value added expense, like either be like wages or anything, it would be the costs.
Right. So we did some trials with that. Like there's some price information in EcoInvent, and we tried to utilize that. But we were not really able to interpret the results. Right. What we did was we did the difference between the price of one process and its inputs and said that this is like the value added, if I understand correctly, right? Is this what you're referring to?
Yeah, you could. Yeah, in EcoInvent you will need to figure the value added because it's not there.
Yeah.
You could, in theory, calculate like you do, like you were doing. Yeah.
Yeah. Exactly, and then you can use that information also. No problem. But there should also be a function for users to supply their own data on prices, right? Before we heard that better to have some data than no data. Of course, we can use this information that is out there, but if our interpretation of the results doesn't lead to anything tangible, we need to look for better data, right? And we want to give the option to add this data.
Cool, thanks.
Thank you. So is there another question? We have 2 more minutes, so maybe one more question in the room. I was wondering, just to follow up on what you said, how do I understand that if you use EcoVent, they have markets already, and all processes only in markets generally. Would you then just erase markets or like some markets up, basically, like their inputs? The inputs. Sorry. Yeah. Sorry. The question was if I would sum up the markets that are already in EcoInvent. The suppliers, exactly, and it's that what I would suggest you to do. Not exclusively. You don't only have to work with markets that are already in EcoInvent. You can specify your own technology mixes in other processes, but in the case study that we present in the paper that is going to be soon available, we are working only with the markets from EcoInvent, with markets from premise, actually. So you can also use prospective data ground databases, whatever you have stored on your system. Exactly. Maybe one final quick question.
And did you do some work on introducing integer variables as well? And is there some point when the X open source format is not like reliable anymore, you would have to switch to robotics?
So the question was about integer problems, introducing integer variables. So we have a branch on playing with that. Currently, it's not supported, integer decisions, but Cplex, at least with the size of variables that you get from EcoInvent, that is the number of processes, there's no problem if you use Cplex as solver. But if you use other open source solvers, it doesn't really, well, you run into problems. Yes. Yeah. Oh, sorry. Thanks for insisting on it. I'm not sure about that because I don't really know how Brightway parameters work, to be honest. So I would need to, I don't know how to to answer to that question since I don't know enough about that. But yeah, they're certainly categorical if I understand it as a choice between different, processes or regions. Not sure. We can talk about this in person if you want.
There's a very strong assumption in your making, but you do have to switch to these.
Yes. Okay. So I think it's time, or if you have any more questions, please feel free to reach out to me. And yeah, thank you.